Hello grade 12s, welcome to my channel. Now let's continue with our lessons on sequences and series. Today we're going to discuss the geometric sequence. Now let's consider the following sequences and add two more terms in each. And of course for each we need to propose a general formula for each sequence. Okay, so now if we study these by inspection, we'll see that to move from 2 to 4, we may have added 2. But to move from 4 to 8, we added yet another 4. So now the difference between these two is not the same, okay? But how about we say we multiplied 2 to 2 to get to 4. And then we say 2 times 4 gives us 8. 8 times 2 gives us 16. 16 times 2 gives us 32. So we can clearly see that we simply are multiplying by a common multiplier to each term to get the next. So we can easily say 32 times 2, which gives us 64. Okay? And we say 64 by 2, that's 128. Okay? And of course, this should go on and on and on. All right? Okay, so we have a common multiplier here. That's what we have of 2. Let's put it that way. Okay, so if we look at the next one, what do we see here? 3, 9, 27, 81. This is 3 by 3, that gives us 9. 9 by 3 gives us 27. 27 by 3 gives us 81. Now, we want to know what is 81 by 3. So, what does that give us? So, we get... what is it? It's 243, right? 243. Let's just check on the calculator. 81 times 3. Yes, it's 243. Okay. Of course, you can do long multiplication, which I was just doing in my head, and you may sound or look smart when actually you are not really. It's not really being smart right there. And then we say 243 by 3. What do we get? And let's do it. 3 by 3 is 9. Right, that would be 12. And then we put a 2 down. Then we transpose the 1. And then we will have 6. And then plus that 1. It's going to be 729, right? Okay, so can you see, guys, you can do this in your head. You see, during practice, you just want to establish what's cooking here. So we've got a common multiplier of 3 there. So these indeed, it's what we call a geometric sequence of events, because we've got a common ratio between any two consecutive terms in terms of division. Okay, but when we say ratio, already mean division, isn't it? Yes. Okay, guys, so now we have done this. Now we need to focus on trying to get the general terms. Now let's have a look. We have 2, 4, 8, 16. I'm gonna cut it at 32 because it's gonna be a bit too long. In fact, let's write it this way. This is going to be 2, 4, 8, 16, 32. All right. Don't know why it's taking a screenshot, this thing. Anyway, so how do we write this? Well, we can see that this is 2 times 1. This is 2 times 2. This is 2 times 2 times 2. This is 2 times 2 times 2 times 2. And this is 2 times 2 times 2 times 2 times 2. Okay, so this is not a very difficult situation. But then let's have a look and see what is going on here. So this we could express as 2 times 2 to the exponent 0, right? Because that would give us 2 times 1. This is 2 times so this is 2 times 2 to the exponent 1. This is 2 times 2 squared, okay? This is 2 times 2 cubed. This is 2 times 2 to the exponent 4. And then this keeps on going like that. Okay. So what do we learn from this? Well, we can see that if we're looking at these exponents, they're increasing by 1 every time. And as they increase by 1, in terms of the terms, look, this was term 1. This is 1 less than the position. Term 2, this exponent is 1 less than that term's position. Term 3, this is 1 less than that term's position. Term 4, that exponent is 1 less than that term's position. Term 5, you can see that that multiplier or whatever that power is of the order that is just 1 less than the term's position. So what can we say? We can make a conclusion and say Tn here is basically 2 times 2 to the exponent. Now when we say Tn, remember that's the nth term. It should be 1 less than that term's position in the same order. Okay, so this is what we can see, guys, by inspection. Then of course we know that n here is an element of natural numbers. We need to not forget this. Okay, goodness, this thing is doing screenshots. Anyway, so what do we notice, guys? We have more of an exponential equation, if we think about it, because this is 2 times the power of base 2 to the exponent minus 1. So essentially, this is an exponential expression. So this is what we can appreciate, that this whole thing is exponential. It's an exponential pattern. This means it fits well on the model y is equal to a times b to the x. Okay, let's forget about this horizontal shift of minus 1. At the end of the day, this is exactly what it fits into. If we take an example of an exponential equation, say y is equal to 2 to the exponent x. Of course, we are suggesting that the a value here is an invisible 1. Okay, so since we don't write 1, we just leave it like that. Okay, hope this is clear. Now we know here that x is an element of all real numbers. And we know that the range here is an element of, let's not even say element of, but y must be greater than 0 because this is non-shifted. So the x-axis becomes the asymptote from understanding functions. Of course, if you have not done the topic, you would probably not know, but we know this. And of course, after this, y is an element of real numbers, while it is like that. So of course, guys, get used to these kinds of restrictions because knowing how to do them as second nature is important. So let's explore and see. Are we going to see the same pattern that we think of? So if we say so we have 0, 1, 2, let's leave it to 3, and maybe say -1 here. Okay, we're gonna have 1, 2, 3, 4, 5, 6, 7, 8, and that's our y, and that's our x-axis. Okay, let's just see what happens when we plug -1 in there. What do we get? We get a half. So this is going to be halfway right there. And when we plug 0 there, we get 1. When we plug -1 there, when we plug 1, we get 2. When we plug 2 there, what do we get? 4. We plug 3, we get 8. Okay, we can appreciate that this is an exponential equation. That goes through like so. Okay, all right, okay. Now, we see that an exponential equation looks like this indeed. All right, so what can we say? We want to study now between these individual terms. What is the ratio? What is the ratio? Of course, I'm just going to choose those. So we can see that the ratio between these, 8 divided by 4 is 2. 4 divided by 2 is 2. 2 divided by 1 is 2. And 1 divided by a half is 2. So we can appreciate that indeed this 2, which was the common ratio right here, is the base of our exponent. Of our power. It's a base of our power. Okay, all right, okay. And we were able to see that we also had something like that. Okay, but now let's see when we put this on the Cartesian plane itself and put it to the test. It's always nice to do so. So that's the origin. That's going to be n. That's going to be Tn. So we have 1, 2, 3, 4, 5, 6, 7, 8. Okay. So I've got 1, 2, 3. Remember, n is an element of natural numbers, so we're not going to go into the negative axis. So this is 2, 4, 8. Okay. Now, let's plot. we saw that we can't have term 0 there, because this whole thing becomes strange. But in any case, it's going to give us a 1, but we're not interested in going that far. So this, when we put 1, what do we get? 2. When we put a 2, what do we get? 4. When we put a 3, what do we get? 8. We can appreciate that we have a graph that is exponential, and it's going through those points. But we need to be able to see how everything works nicely. Okay, great stuff. And we can appreciate, guys, that the common multiplier there, which was 2, is also in that base. And we can see here that indeed the ratio between 8 and 4 is 2. 4 and 2 is 2. Okay, but this one starts on term 1. Again, make a habit, guys, to understand these graphs, because certain questions that you won't really expect which would sound a bit technical come from this. Okay, so this was you and I exploring that first sequence. Okay, so that's not a problem. So in any case, we wanted to find out what could be the general term, and we can see we can retrieve every term in that sequence. We put a 1 in here, we get 2. We put a 2 in there, that's 2 to the 1, which is 2 by 2, that's 4. We put a 3 in there, we get 2 squared, which is 4 times 2, that's 8, and that's that. We get 4 here, it's going to be 4 minus 1, which is 3. 2 cubed is 8 times 2, that's 16. Can you see? We get a 5 in here, we get 2 to the 4, and that is 16 by 2, that's 32. So we can retrieve every term. So this is indeed a general formula. So be in the habit, guys, to use inspection whenever that is possible, just to gain insights into something. Of course, it's not always going to work. Sometimes you will be surprised by the lesson being dropped on you before you are ready for it, so there won't be enough time. But here's what I'm proposing. Please keep going back, and just go right back at the very beginning. Despite having seen what you've seen, having learned what you've learned, see how much more you can uncover by just trying to find out what could be the relationships between this and what I know. Could I use what I already know to really get around this rather than going through with the standard approach? What can I learn from this indeed? And you will see that the lessons will just keep coming. Okay, all right, guys, I'm not going to do the graph for the second one. We're just going to explore the second one for its general term. Okay, this was just the first one. Second one starts with 3, 9, 27, 81, and this keeps on going. So this is the same as 3 times 1. This is 3 times 3, 3 times 3 times 3. Try to use prime factors, okay? The smaller ones. 3 times 3 times 3 times 3. Okay, the most important is to try and show it this way, because we can learn a lot this way. Now we want to keep this very 3. Key is we want to keep this 3, the very first 3, like we have above. We kept the very first 2. Now what do we see here? This is the same as 3 times 3 to the 0. Here this is 3 times 3 to the 1. Here this is 3 times 3 squared. Here this is 3 times 3 cubed. Okay, again we know that this is term 1, term 2, term 3, term 4. Now we can almost appreciate the fact that the position right there, the exponent of the power that we are multiplying to, is essentially 1 less than the position of that term, and it keeps on being the same. We see that the exponent of the power to which we're multiplying the 3 is 1 less than the term's position, and this keeps on going. So what can we say? We can say it seems to suggest that the nth term should be 3 times 3 to the n minus 1, okay? But it should be 1 less than the term's position, right? As you can appreciate the situation right there. And we know that n is an element of natural numbers, and we need to keep that in mind. Of course, guys, I'm not going to do the graphs, but they're just more or less going to be the same thing. If we've studied something and we can see, we can appreciate that the base is the common ratio, and the exponent just is 1 less than the position, and we're multiplying the very first term, because everything stems from that very first term. So this is what we can see. This is what we can do by inspection. And then, of course, there are better ways to do certain things. But now let me just show you something strange. You know, in maths, when you play with the tricks, you start to uncover a whole lot more. Let's just take that example 1. So we had 2, 4, 6, lying, 4, 8, 16, 32, and then this keeps on going. Now, let's say our interest is to try and find out what would be the last term, because remember, the nth term is what we can regard as the last term. So what do we see here? Now, since we saw that we had a common multiplier of 2, this means 4 over 2 was equal to 2. And we can see that essentially 8 over 4 also gave us 2. And we can even see, 16 over 8 gave us 2. And we can see that 32 over 16 gave us 2. But now I want us to notice something here. It's a pity my space was a bit crazy. We can see that we can make this equation 1, equation 2, equation 3, equation 4. Can you see how many terms did we have? 1, 2, 3, 4, and 5. Out of 5 terms, we ended up with 4 equations. All right? Okay, all right. I feel like I need to readjust something here, because I don't like it the way it came out. The way it came out, I'm not quite happy. Okay, let's take this one out of there. I just wanted to write it here. 32 over 16 gave us 2. So we said that was the second equation, third equation, fourth equation. Now in maths, if we decided we're going to multiply every side of this situation, what do we end up with? Just want to see what we're going to come up with. Now, when we multiply here, we end up with essentially 4 over 2 times 8 over 4 times 16 over 8 times 32 over 16. This is equal to, multiplying here, we end up with 2 times 2 times 2 times 2. Now look at the magic. 4 divides 4 to 1, 8 divides 8 to 1, 16 divides 16 to 1. And therefore we end up with 1 times 1 times 1 times 32. So what do we have here? We've got 32 divided by, this is 2 times 1 is just 2, which is equal to, this is 2 to the exponent 4. Now, we just wanted to find out, could we define this term in terms of everything, because that would be the last term. Of course, this is over 1, cross multiply. Therefore, we can see that 32 is indeed 2 times 2 to the exponent 4. Very important. And now what is this term? This is the fifth term. Can you see the exponent is 1 less than that position? Because if we look at this, we say this is n. If we said 4 is n, the term 5 is n, then this would be n minus 1, isn't it? Because 5 minus 1 gives us 4. This is where n is equal to 5, of course. So, yeah, these little things. Anyway, and we would appreciate that this would be n minus 2, this would be n minus 3, this would be n minus 4, right? Right. So again, be in a position to see these expressions, where they come from, by just taking something that you can use. Because if we can take something that we can use, we can move nicely. These are very important to get around, because some students wonder, where did that thing come from? Can you see we can define the last term in terms of the first term, which is 2. And there is that first term right there, because it is still that first term there. Still that first term, we kept it. And then we can appreciate that this became the common multiplier as the base, or the common ratio. And the exponent was 1 less than the position in actual fact. Okay. So these things help a lot to try and do and play around. It maths, certain tricks, because this is just a mathematical trick, but it goes a very long way. All right. Hope you guys have understood and enjoyed that. And the nice thing is that these tools are to the exponent just as many as equations as we could find. We could see that we had 4, and that is 2 to the exponent 4. And if we regarded this as n to the minus 1, that would be n to the minus 1. Okay, remember that. Now the geometric sequence or progression, of course, we saw that it is exponential. Okay, is defined as any sequence where each term is obtained by multiplying the previous by the same constant quantity. You can say same quantity or constant quantity. All right, good. And this constant multiplier, we can say this constant multiplier or quantity is called the common ratio. And we saw that the common ratio essentially was a 2 in this sequence. Okay, not a big deal. Now, the derivation of the general formula for a geometric sequence. How do we do it? Okay, let's consider we've got a geometric progression T1, T2, T3, T4, and then it goes on, and then the very term before the last is going to be Tn minus 1 going to Tn. Now we understand how these things go, because n is an element of natural numbers. We need to understand that. Very important piece to keep in mind, okay? So if n is an element of natural numbers, the term before the last is going to be like that, and then the last term, because we can see that each, what can we say, each term, when something precedes, it comes before, but could we say preceding term? Anyway, we can say each subsequent term is in a position that is essentially 2 more than the preceding term, and that means the preceding term is 1 less than the subsequent term in terms of position, and this is why we are doing what we are doing there. Okay, so logic, guys, needs to not escape you. Now we're going to set up this thing, because we know that there is a common ratio. In fact, let's speak about the common ratio here. The common ratio is such that the term before divided by the term after divided by the term before should give us R. But we need to place a restriction. We never have a term 0 here. So we know that for this setup, we must not have term. We can say n should not be equal to 1. Right? Right, because we will end up with term 0 in the denominator. So we can't have that. So always look at something that you write and essentially appreciate what it stands for. And we know n is an element of natural numbers. Or somebody may say the term that comes next, so tn plus 1 divided by tn, which is the term before, should give us R. Now what could be the restriction here? Like I said, we must never have term 0, so we know that n should not be equal to 0 here. And of course n must be an element of natural numbers. So this is what we understand, guys, that when we have a geometric sequence, we see that the ratio of the 2 consecutive terms gives us a constant ratio every time, and that constant ratio, we call it the common ratio, and it's denoted by the small letter r. Okay, so, and of course there's more than one way to look at something, but pay attention to what restrictions you may need, because the examiners can bring this up and force you in the path that you have not thought about. So always keep an open mind. Okay, so we understand that essentially term 2 divided by term 1 is equal to R. That gives us our first equation. Term 3 divided by term 2 also gives us R. That's our second equation. We know term 4 divided by term 3 gives us R still. All right, and this continues up until we end up with Tn divided by Tn minus 1, which gives us R. But now what would be this equation? We can see that the equation itself, if there's a 4 there, I wrote this wrong. Don't know why I'm not focusing. If there's a 4 there, can you see this is 1 less? So if this is Tn, then this should be 1 less. Nice and easy. Nice and easy. So again, pay attention to patterns, guys. If you don't, you are dead, okay? And I will happily bury you with a wide smile. Now, guys, what are we doing? We're multiplying each side. So it's going to be T2 over T1 multiplied by T3 over T2 multiplied by T4 over T3. multiplied by, in fact here there's a bit of a gap because there's plenty of terms in the same order. That's what we mean by this. Then this is going to be Tn over Tn minus 1. This is equal to, now as many r's as we have multiply each other, so this is going to be r to the n minus 1, isn't it? Because we saw this above. Easy. So we continue. This implies we can see that essentially this divides that to 1 and that divides that to 1, and this will divide something there. This will be divided by something there to exactly 1. And so we end up with 1 times 1 times 1 as many times until we get to Tn. So this means Tn over T1 is equal to r to the n minus 1 all over 1. Now we cross multiply. What do we end up with? Because our job is to define the nth term, which can be regarded as any term in the sequence, or commonly the last term of the sequence. This is going to be T1 times r to the n minus 1. But now we know that T1 is denoted with the letter A. We can then conclude that T sub n is basically A times r to the n minus 1, where n is an element of natural numbers. Okay, good. So this is how we derive. Of course, there's many ways of looking at this, guys, as you have seen what I showed you there. There's many ways of doing this. You could easily do it this way that I've done it, but instead using T1 and seeing that everything is going to be the common ratio multiplying to whatever the result is between T1 and the common ratio, going all the way until the end. At the end of the day, we end up with something that makes sense. Of course, that would be T1, that would be r, that would be n to the minus 1. But this is, something that wants to make a bit of sense in terms of, this is more of a formal thing. But again, doesn't really matter. But for me, guys, this telescoping effect of these terms, was it not there in the paper 1 from November 2024? It was there. The idea was truly there. So essentially, these proofs are not necessarily examinable, but the truth is it's a lie to say it's not examinable, because this very concept was examined in that 1.3. If you didn't know it, you are dead. That's just as simple as that, okay? So, very important to know these kinds of tricks, because they come up in the exams more often than you realize. But of course, you guys almost always want to focus on the same things, always. You don't want to apply your minds a little bit. So sometimes, to give it a bit of, a challenge to yourself, you become the best that you can be. So this is how we can find any term in a geometric sequence. We use this formula, we will always win. Okay, so now we've derived a formula, we can now have a bit of a better structure than to always have to inspect like this, because there are times when this may not really work in our favor. So this protects us from any challenges or failures. So you can see certain tricks lead to something more meaningful. Maybe someone who did this was just playing a game, or noticed this keeps on happening if they do that. But then eventually this formula came about and it became bulletproof. So hey folks, play around with the things and let's see what they bring forth. Anyway, let's do it, and let's look at a worked example to try and now apply what we have just discovered. Question says find the 10th term of the sequence, and of course we will see that technically, essentially, we see that there's a common ratio of 3 here. But when you don't know, you just check and say r is going to be 6 over 2, which is equal to 3. or r is going to be 18 over 6, which is equal to 3. And the moment this thing matches, remember you do this on your rough work because we don't want to see this. This whole shenanigan, we're not interested. It belongs to the rough work, okay? That means it's a side calculation. All we want is you telling us that r is 3. We don't care how you got it. Now, the next thing, what are we trying to do? We're trying to find the 10th term of this sequence. So we can see this sequence is geometric, okay? So perhaps the best way to go about it is to say, therefore, the sequence is a geometric progression with r equal to 3. Maybe it's better because to qualify it is important, and to get r is also important, because what we're going to do next is informed by that identity. Now the next thing we can say then, we know Tn is equal to a times r to the n minus 1. This implies, what are we looking for? The nth term. So we know that the 10th term. Now the first term is a, so that is 2 into r. We have 3 there. That's going to be to the exponent 10 minus 1. And so here I don't want to waste time. T10, we can just put this on the calculator. Let's see, 2 into 3 to the exponent 9 gives us 39366. Okay, again here guys, there's no way of proving this as true or what matters now is to ensure that the substitutions are important and to get the correct answer, because usually this is a 2-mark question, maybe 3 by identifying the sequence and the common ratio, because those are very important. Okay, so this is how this question would be worth. And of course, it's a typical exam question, so be very careful. You may be given a sequence that is not identified. You have to check what it is. From identifying what it is, then give us your verdict. From your verdict, then you need to show us the formula that you are applying in solving the question, and perform correct substitutions, because this is often mark worthy, especially when there's a problem with the answer. You don't want to lose, those 2 marks, because these are the marks you get. But then if you end up with the wrong answer and you only wrote answer only, and now that means you forfeit all these 3 marks, and yet you could have scored some marks even if the answer came out wrong. Perhaps you performed a wrong, insertion of values into your calculator, or the calculator is in the wrong mode. But at the end of the day, if we see how you went about your work, this is where you still score 2 marks out of 3. That's more than 50%, okay? So always, guys, be very careful on how you perform your duties here. Let's take another example. This one is a bit challenging, but we'll get through it. It says now, determine which term of the following sequence, again, we don't know what this sequence is. We need to find its identity, is 4 over 125. Of course, now we know what we're dealing with. We're doing geometric, so I'm going to guess you know. Now let's just find out. Remember again, guys, this step is what you don't really have to show. Minus 4 divided by 20. This is minus 1/5. Or r is equal to 4 over 5 divided by minus 4 over 1. So this is going to be 5. This is going to be 4 over 5 times minus 1 over 4. And the 4's essentially divide to 1, and everything remains as 1/5. And we can see that definitely this is the same thing. So this must be geometric. The reason I just jumped for the common ratio is because I know we're dealing with this pattern. But in the exam, you check whether this is arithmetic, quadratic, or geometric. Those are the three main sequences that we get examined on. So that is the check for the student. Again, guys, this must be part of your rough work, meaning it should not feature. Here we can just get the verdict that this is what is that now? This is a geometric progression with r equal to minus 1 over 5. This is very important because this is a mark, because identifying what we have, we score a mark there. Now our job is very easy. Then we know that Tn is equal to a times r to the n minus 1. Why do we know this? It's because we said this is a geometric progression. Now we know what is the nth term. It's 4 over 125. Now we are saying this, the a is the first term, which is 20, into r, which is minus 1 over 5, to the n minus 1, because that's what we want. The question is, who is the stud? So that's where the question mark is. We need to find that. Okay, so let's move on. This implies we divide by 20. Okay, maybe let's show it. We divide by 20 on both sides because I'm trying to isolate this power. So if we divide by 20, we are essentially going to say 4 divided by 125 times 20. So 4 divided by 125 times 20, that's what it's going to end up as. So as a whole, on the calculator, sometimes use your calculator to free yourself from some trouble. So this is 1 over 625 equals minus 1 over 5 to the n minus 1. Okay, so question is, can we express this 625 as 5? Let's check it out. Okay, I'm running out of space. So we can say 625 equals 625, and then we press shift. Fact, this will give us this thing in terms of its what we call prime factors. So this one is actually 5 to the exponent 4. Okay, that's good. So this implies that we have 1 over 5 to the exponent 4. This should be equal to minus 1/5 to the exponent n minus 1. Now we have a challenge here. Our challenge is that this base is negative, but that one is positive. But now here's the thing. If the exponent is even, when the exponent is even, it implies that the base is either positive or negative for the same positive answer. Right? So this is something, guys, you'll probably not notice, because sometimes in some textbooks or even in just general teaching is not often highlighted. So just remember, once we have an even exponent, it means the base can either be positive or negative, but the resulting answer is going to be positive. Please know these things. This is why I flagged this one with an asterisk, because it's a very good question in that it tells us we need to be creative as we solve, because even if you just try to apply logs directly, this would fail, because log of a negative number is undefined, but this has a solution. So this means we have minus 1 over 5 to the exponent 4 into minus 1 over 5. Because the bases have to be the same for us to drop them. Okay, this also implies now we've got two powers that are equal. They have the same base. It also means the exponents should be equal. All right. Okay, all right. So we can say, therefore, n is equal to 5. Because when we transpose that, it adds there. And to answer the question, we can say, therefore, T5 is equal to 4 over 125. Sorry. Okay. I just got squashed here a bit. Otherwise, we have answered the problem. Of course, this is also part of the rough work. We don't want to show it in our script. But given a booklet, you can just split maybe a portion of it and call it RW. So you perform all of these things. And sometimes when you realize you are losing time, but your rough work is perfect, you can just write the CRW. Then they will check and mark you there. Seeing that it's rough work, it means if you have not directed the examiner to your rough work, then they will not look at it as an answer, because they will follow what you wrote down in terms of a number. But if you realize time is against you and your rough work is perfect to answer the question, just write the number there and say CRW. And go to that RW and mark that question with the right number as well. Then it will be marked for that question. So be very flexible. Don't be like ungabili hashe elifaka amakopo. Wabona amahashi lawa awatrippelayo xa kunemicimbi. Faka amakopo abona phambili qha ayibone ecaleni. No, don't do that. Look around and turn around. Give me the 360. Anyway, this is the story, guys. So again, correct substitutions, folks, is mark worthy in maths usually, and we can get the answer there. Again, this would be maybe worth 4 marks because of this, because that's some extra stuff, because this is a spice you would not be prepared for. So that would essentially be an extra mark. Again, this comes from understanding these expressions. In grade 12, guys, we need to be in a position to show ourselves as having gone through the previous grades properly. We didn't just get pushed. And then bazofika bathi abantu aba-progressed baye bapasa kakhulu. Hey guys, animeni kancinci. Sometimes ezinye izinto zindenza ndibe ne-worry, because how can you progress someone ofele igrade e-before agqiba azopasa with distinction kwigrade elandelayo? Akho sense lapho. Andiyivi sense. But again, there's 2, maybe 3 arguments for that. One, we can say the teacher in the previous grade was horrible, because we can't place the student in there, because not the same student in 2 different classes performs differently. Okay? There's no way. So if the student shows up performing different, it means the teacher is horrible, especially the one in the previous grade. Okay? Or the teacher in the second grade is cheating. Okay? Because they saw this one is weak, but they want to maintain their 100%. Perhaps they just cooked marks for this one so that they can pass well. Because they know they're not too bad after all, but they were not that good, to be honest. Anyway, that's the second scenario. And then the third scenario, it means the person actually upped their level. They realized their nonsense if they were just being silly. But there are some people who are very gifted, but then they tend to take things for granted. And maybe it could be the reason they somewhat fell off the path. And now they realized in grade 12, okay, guys, this is it. It's a do or die. My situation needs to be rescued. And then they came back to their senses. So those are the 3 possibilities for me. But let me tell you guys, the first possibility, that the previous teacher must have been horrible, is probably the stronger one. And the one that the student was playing is the second strong point of view. The third one is highly unlikely, although we know such things are done, as unfair as they look. Because those guys don't make it in first year university where there's no way of cheating. But hey, people always find a way of cheating the system, isn't it? Because if they're moneyed, they'll just go and pay the professor there to make it worth their while. You won't believe what happened in our university. A whole lot of people, a certain race by the way, was copying 100%, and it was discovered. And we saw them crumble when the things changed. But we are not about that at the moment, because even our folks were also caught in the mix, because they like easy things, these ones. They don't even realize they're destroying their own futures. Anyway, guys, enough of the nonsense. I hope you are enjoying the lessons. Let's just move on a bit faster. Now, example 3, we need to find the first term. We are given that the first term of a geometric progression. Now, here's the good thing. Sometimes an identity is given, meaning what are we dealing with, is 5, and the fourth term is 40. Okay, so we're given the first term as 5 and the fourth term as 40. Now we need to determine the second and the third terms of the sequence. That's very easy. We can answer here and say answer or solution. I should have been writing that as I went along, but hey, who cares? Who cares? Because we need to indicate that now we are solving. Yeah, guys, you will find yourself a space to write that for yourselves. By the way, in the description, I will attach this document just in case you want to look at it again and play with these questions without looking at the video, which I recommend highly. The reason why I put these documents in there is for you guys to use these for reference, and also to try and get these questions, solve them without looking, and look at the hard copy of answers, because sometimes you may not have data when you really need to check this out again. So be very friendly to yourselves. Okay, so guys, in a geometric progression, we know that Tn is equal to a to the n minus 1. This is the generic formula now that we know. But of course, guys, we know that if we're saying T1, that's just a. So we don't have a problem. We know that a is equal to 5. Can make this one equation 1. And we know that the fourth term is going to be AR cubed, because the exponent is going to be 1 less than the position, right? Is equal to 40. Now, this is when you have mastered your work. You don't need to start here. But this whole shenanigan can easily come from there. All right, so now what are we going to do? We can say put 1 into 2. So what are we going to see? A is 5 into r cubed. Okay, maybe let's not be silly. Why do I need brackets? 5 times r cubed is equal to 40. And then we divide by 5 throughout. We get r cubed is equal to, now 40 divided by 5, that's 8. Okay, great. So this implies that we have r cubed. Now once we see this exponent, can we show 8 as a power of base something to the exponent 3? Yes, indeed. It's 2 cubed. And so once the powers are equal and they have the same exponents, it means the bases must be the same. Therefore, r is equal to 2. Because without this, we would not know how to move around. Right. So let's get to this business now. We want to find the second and the third terms. We can say then, now we know that the second term, T2, is going to be AR, which is going to be equal to 5 times 2, which is 10. And so T3 is going to be, this time I'm not going to write this, it's basically T2 times R. This is 10 times 2, which is 20. There are very easy ways. I mean, you can still use this formula. You can still use that formula. It's not a big deal, just to make sure everything is smooth. Alright guys, so we get a mark for each one of those because that's the answer. Finding R, it's a mark. Substituting one into the other, it's a mark. And essentially this could be worth 4 marks. Usually the gymnastic is applied at this point, so not so much. But if one is feeling kind enough, then we do that. So guys, again, this highlights the concept of simultaneous equations. So we don't learn these in algebra for just fun, okay? We learn these so that we can use them later on. All right, let's take another example. Wow, so much space. Crazy. Now let's look at example 4. Now we are told if, this is if, if x plus 1 is to x minus 1 and x are the first 3 terms of a geometric progression. Again, look at the signature, because when something like this is given, we will always be told the actual identity of what we are looking at, because there's no way we could proceed if we don't know. Now we are told to find x and the first 3 terms of the sequence. Okay, let's deal with the solution. We know that the geometric progression is such that we have x plus 1 is to x minus 1 is to x, and it keeps on going. Since we know this is a geometric progression, we know that x minus 1 divided by x plus 1 should be equal to x divided by x minus 1. Can you see we're being smart here now? Why? We know that each ratio is equal to r, which is the common ratio, and so that's why those two are equal. Now, gymnastic of choice, cross multiplication. This implies that we've got x minus 1 all squared equals x into x plus 1. And then we then follow up nicely as we know how to deal algebra. This is x squared minus 2x plus 1 equals x squared plus x. Now we can see that this and that are the same sign on either side of the equal sign. Again, a grade 12 student should know this, second nature. Now we just transpose this minus 2x to that side. We end up with 3x is equal to 1. Therefore, x is a third. Nice and easy when we divide by 3 on both sides. So we have found the value of x. Okay, and now this is a very critical step, because there's no way we would proceed if we didn't know that. And now creating that equation and justifying for it, because you can't just write. No, we don't promote guesswork, because guessing right is not, we're not here about just giving marks for the sake of giving marks. If you just write things that you don't justify, for me it's either you copied or you're guessing, and those two don't deserve a mark at all, because then we are essentially wasting our time teaching you if you're going to go around guessing, because the exam is standard, or it's standardized. Okay guys, so we've solved for x. So what we want now, we can say therefore, we can say then the geometric progression is going to be a third plus 1 into a third minus 1 into a third. Okay, and then it keeps on going. You can say therefore the GP Multiply 3 there, that's 3 plus 1, that's 4 over 3. Multiply 3 there, 1 minus 3, it's minus 2 over 3. And that's just a third. So that is the story, guys. Those are the first 3 terms of the geometric progression. So we've done it. It's answered. Is delivered. Now, folks, all we get here is probably the answer. There's not so much to score here. So that could be just 1 mark. Okay? Not a big deal. So we have a total of 1, 2, 3 marks. Makes sense. It makes sense. Again, this is the concept of simultaneous equations, but we're just coming up with a smart way of showing how to go around things. Instead of deriving one equation and then deriving another equation and then putting one into the other or equating the two, doesn't really matter, guys. You can do whatever you want, but there are smarter ways of doing things. That's just what I'm trying to emphasize here. Now let's get another example, guys, so that we can finish this thing. Now, given a geometric progression, again, we have the identity of what this is. We need to find the value or values of P and Q. So there is P and there is Q. So if this is a geometric progression, what are we going to do? Solutions. Now let's have a look. We know, guys, for a fact that technically P, maybe let's just say this is A. We know that P is going to be equal to plus or minus the square root of 5 times 20. Holy cross. Therefore, P is going to be equal to plus or minus 10, isn't it? Because that would be 100. Ne? But now, guys, we need to pick the right answer. Remember, the question said value or values. But now, if we look at the next term here, it is positive. So this term cannot be negative. So we will drop the negative. Very important. I'll tell you why I know this in a moment. So there are certain ways. Here I'm just trying to add a particular concept. So this one is introducing a particular concept that needs to be understood as well. So it also follows that Q is going to be equal to plus or minus the square root of essentially 20 times 80. Right. So therefore Q is going to be equal to plus or minus. Now what is 20 by 80? You can do it using a long multiplication, but at times you need to save time. It's easy to do it because you know what I used to do? Naga, I have tricks, guys, like lots and lots of tricks. I'm a very crazy guy. I'll just take this number and multiply that number. And then I would have 16. And then I maintain the zeros. So that's 1,600. Very easy. You know? That's what I do. Okay. But again, guys, this is just me. Those tricks are not bulletproof sometimes. Be very careful. But, you know, sometimes in life, there are certain shortcuts that work. So be very careful. I only do it when I have, like, you see, digits like this. You know, where there's just double digits, 2, 2, and then there's zeros on the other end. Or triple digits, but there's zeros that are balancing. So I always do that because for me, that's how quickly I can get to the answer. And of course, it would look smart, but hey, you're not smart. You're just using a trick. Anyway, so what's the square root of 1,600? It's like the square root of 16. That would be 4. And then you just drop 1 0 here. It becomes 40. So this is 40. Okay. Again, guys, let's look back. Is it possible for this to be negative? No. Because we can appreciate that our common ratio here is not necessarily negative. So all these terms are positive. So there's no way we can have a term that is negative here. Nice and easy. So those are the ways we do things here. Now guys, you may be wondering, how did I know this is the case? Now there's two ways of thinking about it. The reason for this is perhaps using the common ratio, the idea of the common ratio. Because we know, guys, that 20 over p, okay, maybe let's start like this. We know that p over 5 is the same as 20 over p, because each is equal to r, isn't it? Yes, when we cross multiply here, what do we get? P squared is 5 times 20. And so it makes sense to say p is the square root of 5 times 20. Right. That's exactly how I know. But there's another reason beyond this. Yes, we're using this for sure, but now what is the actual explanation? Now let me give you now. If, say for example, A, B, and C, okay, maybe let's do this. If A, B, and C are the first three, they are the first, okay, let me relax a bit. They are the first three terms of a geometric progression. Therefore, we know that B is going to be plus or minus the square root of A times C, right? And we call B the so-called geometric mean. Ah, that's the one. We are using the concept of a geometric mean. So please be aware of this thing, because I hardly see it being taught. If it is, well, good for those who see it, but people tend to neglect these small things, and they have a very, 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 very important, part to play in the long run. So this introduces the concept of the geometric mean. Please read about it if you can. It's not a big deal. I mean, I've just introduced it instead of talking about it. So I just wanted to show it in action. So this means any term here is going to be equal to the square root of the product of the terms that actually bestride it. Okay. Or the terms that are colossal to it, like, the Colossus statue in Rome. Back in the days, of course, of Julius Caesar. I don't know if they still have it. Never went to Rome anyway, so let me not speak like I know. I just heard in Shakespeare's book, when Julius Caesar came home and Pompey wasn't happy. The rivalry between two maggots. One was more better because Julius Caesar was arrogant, yes, but the man was principled at the same time. That's why he was so arrogant. Even referred to himself as a third person, Maybe I must adopt that arrogance. Maybe. It might just fit me, Yeah, man, it just might fit me. Because I'm that arrogant dude who is also nice at the same time. Whatever. Anyway, let's just take our last example, guys, and cut this video before it becomes too long. Now, example 6 says, consider the following geometric sequence. Again, we are given the identity of the sequence. So we know what to do now. We're going to use the idea of the common ratio or whatever we want. Now let's have a look. We've got 4, P, Q, and 13,5, okay? Of course, this may go on and on whatsoever. Now we are to determine the value or values of P and Q. So now this one is a bit challenging, isn't it? Because it's not as straightforward, because we could easily use the geometric mean issue here and even there derive simultaneous equations, wara. But it's gonna hurt, you know. So we don't wanna get hurt. There's no need, you know. There's no need to get hurt. So what are we going to do, guys? Here's what we need to do. We know that this is term 1. So again here, this is where flexibility comes in. This is term 4, and we know the value of term 4. Because term 1 alone doesn't help us, you see. Term 1 is not very useful alone, but any term after that can be very useful. So what do we know, guys? We know from here, okay, let's just write solutions. We understand that here technically Tn is a times r to the n minus 1. That's our working frame right there. And we're going to use it. Now we know term 4. So we know that term 4 is equal to 13,5. What does this imply? It implies term 4 is going to be a, which is 4 times r, which we don't know. But now r is going to be 1 less than the position. That is 13,5. See, we don't need to sweat. Of course, you can use this formula directly, but at this point, I do not have the time. Okay, so we divide by 4 on both sides. What are we going to end up with? R cubed is equal to, let's see, 13.5 divided by 4. That's, let's see, that's what 27 over 8. Let's leave it at that. So this is 27 over 8. Now we can see that the exponent is trying to lead us somewhere. Can we express 27 over 8 as some base to the exponent 3? The answer is a hell yeah. That can be done, because we know this is 3 over 2 cubed. Now once the exponents are the same and these powers are the same, we know that the base should be 3 over 2. Nice and easy. Since we have a comma there, this should be 1,5, isn't it? Yeah, we can say therefore P is the second term, so it's going to be a times 1,5. What do we get? Why did I write a now? A was 4. 4 times 1,5 is 6. And therefore Q also is going to be the next one, which is 6 times 1,5, provided that answer is correct. That gives us 9. All right. So those are the two solutions. Okay, so guys, you can appreciate that there's a lot to learn, but we're going to cut it here. So at some point, a serious substitution. Of course, guys, it is very important though to indicate, you know, what we are using. But I do believe that once we know this is geometric, this is more like saying it. But sometimes it's a bit controversial when you don't show what you have used in determining your answers. Remember, in the exam, we are given a clear instruction that we need to show everything we have used in determining our answers. That means from a formula to a reason to some logical thought, whatever it is, some diagram, some graph, some whatever. We have to show it so that we are understood to be doing this ourselves, because there's lots of copying, guys, that we need to guard against. And the moment we get an indication that someone has copied, we don't care if you actually did or did not, because by not following instructions, they're actually trying to tell us that you may have actually copied. And so we don't care even if you got it right. Do you understand? I hope you do. Anyway, it was important to get the common ratio and to get these ones. So this could be very easy 4 marks. And that's the end of our lesson, guys. All right. So I hope you've enjoyed the lesson and that you are going to practice. I will attach this document in the description if you are interested in having it as part of your arsenal in attending to math problems. And please watch these videos, guys, not passively. Try to participate. Try to get your hands dirty and see how far you will go. And you will see how easy the learning experience is going to be. Because at this point, you should not necessarily be learning a lot. You should be uncovering a lot of things and putting things together. That's the essence of matric, so that as you proceed to higher learning or institutions of higher learning, you are ready. You have sorted the foundation nicely, because with this you can do a lot of things. But if this is shaky, you will go on to varsity and just go through the motions. Yes, you may pass because it's easy to follow, the standards, but you will not be a problem solver. And unfortunately, when it comes to work, you will be one of those who sit at home with their degrees. Not that I'm enjoying this, guys. It's a very, very nasty situation to find people sitting at home without, getting work, and yet they have gone to school for plus minus 5 years, 6 years or so. They have all these qualifications, but they can't put them to use. It's not nice, but let's face it, guys, people who are determined, people who really have a purpose for what they went to study, and they truly understood, they don't really struggle that much to get work. They still struggle, but not that much. Not to a point of sitting at home for 2-3 years not finding a job. It means you're not serious. In fact, whatever you studied, it's either it's useless or you are useless. Because it's easy to pass, as I said. To follow standards, it's pretty easy. Cheat through the system is very easy. But the outcomes are what tells us what exactly was going on. So don't be like one of those people. Choose what you can handle and do it well when you're given a chance to do it, because you'll never have another chance. So that as you come out, you can see more opportunities open up before you, and you just pick and choose. Of course, it's not as easy as I'm putting it, but it sure will take you some distance in your career path, and as well as, in improving your life and those around you. Otherwise, guys, leave a like. May consider subscribing if you feel you're learning the best here, and there's more in the channel. And of course, I do full videos mainly, full question papers mainly. You will see that they are the most in the channel. So, so look at those question papers and see how to answer. Because again, I'm not just showing you the solutions, I'm also showing you how to answer best, while at the same time showing you the solutions and the reasons behind those solutions. Okay. Of course, there's mistakes along the way. Unfortunately, I do not have a third person who I can do my solutions first and then send this to, so that they can, become unbiased in evaluating my work and critically analyzing it, so that they can pick up some mistake or perhaps certain things that are not as proper as they should be, so that by the time the video is out, it's edited well. Again, I do not know how to do those kind of things, how to edit a video. Sometimes I pick those up eventually, but because of the lack of skill, I just leave it, and I hope the student will understand. If they don't, please ask a question in the comment section. And of course, if you check in the description of the channel itself, you'll see my contacts there. You can just WhatsApp me if you find something strange that I said, because I do say a whole lot of strange things. Sometimes I don't hear myself, I'd be talking about the first term and then call it the second term or something like that. Very crazy stuff. It's funny how stupid things like to creep in unnoticed, and yet big and beautiful things always want to be dragged out of a hole somewhere in hell, Anyway, guys, goodbye. I'll see you again next time.